Hi there, this is Jude Socrates. Welcome to today's video where we will talk about the limit comparison test. In the last video, we talked about the ordinary comparison test. So this is a different version. Maybe it's an extraordinary comparison test. Just kidding. In this kind of test, as the name implies, we're going to need the limit of something. So before we discuss this topic, which will be in section 2F of our textbook, and again, if you don't have a copy, just go to the description on YouTube and you will see a link to Dropbox where you can download a copy of my textbook. But before we do that, let's review a couple of things. So in order to spare ourselves from going back and forth, let's review some common infinite series that we know converge or diverge, right? So when we talked about the integral test, we saw that summation of 1 over n to the 7/5 converges. These are all p series, and p here is bigger than 1, and we know in general that the p series converges if the exponent p is bigger than 1. If the exponent is between 0 and 1, like summation 1 over n to the 5/7, this series diverges to infinity. If the exponent is exactly equal to 1, and by the way, this has a name, it's called the harmonic series, diverges to infinity. So in this case, the integral is not based on the power rule, but rather is the logarithm. We also saw that for a geometric series, in an earlier video, the geometric series converges if and only if the common ratio r is less than 1 in absolute values. Okay, so let's go to our textbook and let's review this time the ordinary comparison test. Here we go. The ordinary comparison test tells us that suppose we have a sequence of non-negative terms. They could be 0, but most of the terms will be positive. Maybe all of the terms are positive. Now, if we can find a second sequence, b sub n, so that a sub n is smaller or equal to b sub n for all n at least k, the starting term of the sequence, and the bigger, the infinite series made of these bigger terms converges, then our series, summation a sub n, also converges, right? So in plain English, we said, if a bigger series converges, then the smaller series converges also. Conversely, if instead we can find another non-negative sequence, let's call them c sub n this time, where a sub n is at least c sub n for all n at least k, and the smaller series, summation c sub n, diverges to infinity. It has to diverge to infinity because it cannot just diverge. The terms are all positive, okay, or at least 0. Then our bigger series must also diverge to infinity. So if the smaller series diverges to infinity, then the bigger series diverges to infinity also. Okay, so if you haven't seen the video on the ordinary comparison test, why don't you check it out now and then come back to this video. Let us now see the statement of the limit comparison test. All right, here is the limit comparison test, also abbreviated as the LCT. Suppose we have two sequences, a sub n and b sub n, and they're both positive sequences. Okay, let's not allow 0, let's not allow negative numbers. And we know that the quotient an over bn has a limit at infinity, and this limit is L. Now, because we're taking the quotient of two positive numbers, that quotient will also stay positive, so that limit cannot be negative. It is either 0 or a positive number, or maybe it's positive infinity. Okay, so we have those three possibilities in these three cases. The first case is the most general case. If this limit is an ordinary positive real number, like 7 or 1 or pi, then the two series made of these terms, summation n equals k to infinity, a sub n, and summation n equals k to infinity, b sub n, either both converge or they both diverge to infinity. Right? So notice the difference. We're taking a limit. We're not saying that one is smaller than the other or bigger than the other. When that limit is an ordinary positive real number, the two series either both converge or they both diverge to infinity. They do the same thing. They behave in the same way. Now, it's a little bit trickier when your limit is not an ordinary positive number, when it's 0 or positive infinity. But you can still make a conclusion. If the limit is 0 and the series made of the b sub n's, the one in the denominator, converges, then the series made of the a sub n's, the sequence in the numerator, also converges. All right? When the limit is 0 and summation bn converges, then summation an also converges. Bn is the sequence in the denominator, an sequence in the numerator. Last case. If the limit were infinity, okay, so this quotient is approaching a very big number. It's getting bigger and bigger. It's not approaching a big number at all. It's getting bigger and bigger without bound. And the series in the denominator, same as part B, summation bn diverges to infinity, then the series in the numerator also diverges to infinity. Okay, so you have to be careful with part B and part C. All right, so remember in the ordinary comparison test, we said that the bigger series has to converge for the smaller series to converge. If the bigger series diverges, we can't say anything about the smaller series. It can converge or diverge. Okay. So we will go back to the PDF for the proof, but for now, let's go back to our workroom and let's do an example or two. Okay, so our first two examples will be based on something we saw in the OCT video. We saw this infinite series where summation n equals 1 to infinity cosine 1 over n to the 5 over 7, right? And what did we do there? We said that this is bigger than 1/2, so the series is bigger than 1/2 over n to the 5 over 7. We just reviewed that summation 1 over n to the 5 over 7 is divergent, and so our bigger series, this guy is bigger than summation 1 over n to the 5 over 7, must also diverge. Okay, so this time let us consider, let's turn the 5 over 7 into 7/5. Okay, and we saw that this series also converges this time by the same reasoning, except that cosine is smaller than 1. Okay, what we're going to do is we are going to turn cosine into sine. Okay, so yeah, that completely changes the problem because sine and cosine behave very differently as n gets bigger and bigger if you have 1 over n over here. Sine of 1 over 100, what is that? Ooh, it's very small. There's a 10 to the minus 3 there. Okay, that's because as the angle gets smaller and smaller, the sine, which is the y-coordinate, gets closer and closer to 0. Okay? All right. So the numerator, yeah, we don't have much control over it. It's getting close to 0. We can't say it's bigger than 1/2, smaller than 1. Okay, yeah, that works. So you know what? Yeah, let's keep it at 5 over 7. Okay, this one's more interesting. So yeah, even though that is smaller than 1, once again, it's going to be smaller than 1 over n to the 5 over 7, but we just said, if the bigger series diverges, we cannot say that the smaller series diverges also. Maybe it converges, okay? So we don't know anything about this thing over here, except it's getting smaller and smaller, okay? So we do know something about it, okay? Recall that we have a famous limit. All right, here's our famous limit. I hope you remember this from basic calculus. What is the limit as x approaches 0 of sine x over just x? Okay, so we saw that as n is getting bigger, 1 over n is getting smaller, 1 over 100, that's a small number, its sine is also a small number. What is the limit as x goes to 0 of sine of x over x? Okay, I hope you remember that limit is equal to 1. And if you forgot, we did do L'Hopital's rule, remember? That one you should never forget. We have a 0 over 0 indeterminate form. So by L'Hopital's rule, we can take the limit where we get the derivative of sine and the derivative of x, take the quotient. We'll get cosine x over 1, but as x goes to 0, cosine x approaches 1. All right, so that limit is equal to 1. So in fact, in physics, and I'm not a physicist or a physics teacher, this is often used as the small angle approximation. In other words, sine of x is approximately x itself when x is very small. Check it out, sine of 1 over 100, that's 0.01. This is 0.009999 something, which is practically 0.001. I'm sorry, 0.01. Right? So this number is very close to this number. So how does that help us with our infinite series? Sine of 1 over n is therefore approximately just 1 over n. Remember, the hard part in using the ordinary comparison test was, okay, who is this b sub n? Who is this c sub n? Right? Fortunately, for the limit comparison test, we only have a b sub n. But we need to make sure that the quotient an over bn approaches a limit. It should not be does not exist, in other words. Okay? So this small angle approximation will help us to find the b sub n. Right? So just to be clear, in the statement of the LCP, we will let a sub n be our series. Okay, the terms making up our series. The terms of our series. And we will let b sub n be, instead of sine of 1 over n, we will approximate sine of 1 over n with just 1 over n. Okay? Sine of 1 over 100 is very close to 1 over 100 itself. Okay, so this can be simplified. That's the crucial step. Don't just leave it as 1 over n over n to the 5/7, because that 1 over n can go to the denominator. Okay, rules of exponents. Bring the n down to the denominator. And now, rules of exponents, that's n to the 1 times n to the 5 over 7. So we add them together. 1 plus 5 over 7 is 5 plus 7, 12. So we will get 1 over n to the power 12 over 7. Okay. What that is, again, a p-series. All right, but this time, instead of 5 over 7, the p is 12 over 7. Okay, so we didn't see this p-series in the previous video. We had 7 over 5. Okay, So that p though is still bigger than 1. So we know that summation n equals 1 to infinity of 1 over n to the 12 over 7 is a convergent p-series. Okay, but we're not yet done, because we want to make sure that the limit of an over bn must be a positive number. We could also use 0 and infinity, but in this case, because of the way we chose what second sequence to compare to, we're going to get a nice limit. Okay, so now we must check. So we want limit as n approaches infinity. Pardon me, I had to go backstage to get this symbol over here. Limit as n goes to infinity of the quotient an over bn. So our an is our given terms, so we'll replace an with this in the numerator. And our b sub n is this, which we'll replace in the denominator. Okay? And of course, we know how to divide fractions. So we're going to need the limit of this fraction times this flipped over. But if we flip that over, we're simply going to get n to the 12 over 7, reciprocal of the reciprocal. Okay, but what are we going to get here? All right, so we keep going. We can simplify this further. Again, rules of exponents. N to the 12 over 7 over n to the 5 over 7. 12 over 7 minus 5 over 7 is 7 over 7. Okay, so that is n to the 1 in the numerator, which is of course simply n. Goodbye. Okay, but now here's the thing. We have sine of 1 over n times n. We flip this n back into the denominator. So it's just temporarily up there. Normally we don't like negative exponents. But check it out. If we flip it in the denominator as n to the minus 1, that's the same as 1 over n. Haha! And so we are back to the limit that started it all. Limit of sine of 1 over n over 1 to the n, 1 over n, as n goes to infinity. Again, that goes to 0, that goes to 0. We practically have this same limit, right? And again, if you don't believe me, well, we can apply L'Hopital's rule, and we should get 1 just like before. Okay, so by L'Hopital's rule, we will get, where's my arrow? There's my arrow over there. It will go to cosine 1 over n times the derivative of 1 over n, which is minus 1 over n squared, divided by the derivative of 1 over n, which is minus 1 over n squared also. So these two are going to cancel. We are left with cosine 1 over n. As n goes to infinity, 1 over n goes to 0. Cosine of 0 is 1. We get the same limit as before. Okay, let's put it on the next line so that we can clearly see that that limit is equal to 1. All right, so we are in part A of the limit comparison test. We have that the ratio an over bn has limit 1, which is a nice positive number, probably the simplest positive number we can have, and it will show up a lot. If we make the right choice, that limit should be 1, or maybe it's the coefficient of one of the terms. More on that later. All right, so according to part A, both series, summation an, our series, and summation bn, this p-series, both converge or both diverge. But we know that this series is a convergence p-series, so therefore our series this time converges, right? So before, when we had this cosine 1 over n to the 5 over 7, that was a divergent infinite series. Replace the cosine with sine. We needed something else, a different kind of limit. We needed this, sine x over x. This time, it is a convergent series. All right, so since summation of the Bn is a convergent p-series, by part A of the LCT, our series, which is summation sine of 1 over n, must also converge. According to part A, both series summation an and summation bn must converge, or both by diverge. Both must diverge. We know that our b sub n is convergent, so therefore our a sub n series must also be convergent. Must also converge. All right, so our PDF, and let's see the proof for the limit comparison test. So it talks about the limit of an over bn, where in part A, we get an ordinary positive real number L. Okay, so we first saw the precise definition of a limit of a sequence in section 1a. So let's bring it back. I just cut and pasted this literally from section 1a. We say that an infinite sequence a sub n converges to a limit L, written as limit as n approaches infinity of a sub n equals L, if for every positive number epsilon, no matter how small, we can find a positive number capital N, such that if the index little n is bigger than capital N, then the absolute value of the difference, a sub n minus the limit, must be smaller than epsilon, right? So this means that if you draw the horizontal asymptote, y equals L, then eventually the terms will be within an epsilon strip around that limit L. Don't worry, we're going to see a diagram in a minute referring to this proof. We have not a sub n though, but a sub n over L. So let us rewrite that limit definition. And since it's supposed to work for any epsilon, we're going to pick a very convenient value for epsilon that will help us complete the proof. L is positive, so let's make epsilon L over 2, half of epsilon. The definition now says, if little n is bigger than capital N, then not a sub n, but a sub n over b sub n minus L is less than our epsilon, which is L over 2, right? So you're going to say, where did that L over 2 come from? Why is that? It's because it works. Let's show you. Could we have picked another epsilon? Maybe, maybe not. But if it works, it works. So let's see why it works. The inequality with absolute values can be written without absolute values. Take away the absolute values. Whatever is inside must be between minus L over 2 and positive L over 2. Okay, definition of absolute value inequalities. Now, let's move the minus L to the other sides. Add L to all parts of this inequality. So you get L minus L over 2. L is gone. L plus L over 2. But now we get L over 2 on the left, simplifying 3L over 2 on the right. Okay, so this tells us, because Bn is positive, we can also get rid of the b sub n in the middle, multiply all three parts by b sub n. So we get L over 2 times b sub n is less than an and less than 3L over 2 times b sub n. Okay, so this third inequality can be visualized using our epsilon strip. And here's the beautiful diagram over here, of course, thanks to GeoGebra. Okay, here's our x-axis, or I should say our n-axis. And here's the limit L. That's my dog. Sorry about that. The dog freaks out when the doorbell rings. It's my neighbor. Anyway, how can we visualize this third inequality? Okay, we will plot the terms an over bn, and they have to be trapped between L over 2 and 3L over 2. Okay, so we said, all right, here's the n-axis. The limit is over here. This is y equals L, but I didn't draw it. I'm sorry. Oh, yeah, that is the L. And so half of this is L over 2, which means that I will add L over 2 up there to get 3L over 2. Okay, so here's the limit L, and if you wait long enough, the terms an over bn, you're getting closer and closer to L, so they're between L over 2 and 3L over 2. Okay, so now the ordinary comparison test comes in. Our terms are between L over 2 bn and 3L over 2 bn, the second sequence. Okay, so b sub n is a positive sequence, and let's scoot this up over here. So what's going to happen? There are two possibilities. Either the series made by the b sub n converges or diverges to infinity. All the terms are positive, so it can only do one of those two things. First case, if the series converges, then summation 3L over 2 also converges, because that's just a constant. But our terms are smaller than 3L over 2 times bn. So by the ordinary comparison test, our series also converges, according to part A of the OCT. Flip side, what if the other series diverges to infinity? Well, this time L over 2 bn, the summation, also diverges to infinity. But this time, an is bigger than L over 2 times bn. And since an is bigger than a divergent series, the an must also be a divergent series. In other words, summation an and summation bn either both converge or they both diverge to infinity. Yay! Okay, so let's talk about part B. What if the limit of the quotient is now 0 and the series made from the denominators converges? Okay, well, this is much easier. If this limit is 0, well, that means that the fraction is eventually going to be smaller than 1, right? Which means that the numerator has to be smaller than the denominator. Okay, we have a fraction here. It's getting smaller and smaller. So therefore, the numerator must eventually be smaller than the denominator. All right, but we know that the series made from the denominators converges. So therefore, the series that we have, summation of a sub n, must also converge by the OCT. All right, and of course, part C is also proven in a similar way. Let's do another example. When we did the ordinary comparison theorem, we saw this infinite series. Okay, so instead of cosine 1 over n, we had ln of n over n to the 5 over 7. Okay, this time let us consider, I'm going to take this and I will put the ln of n in the denominator. Ooh. So just to be sure, let's put a times symbol in between there. Aha. I have exported the ln of n down to the denominator. Okay? So In that video, in our last video on the OCT, we used this very powerful property that for any positive number k, ln of n is going to be smaller than n to that k if n is big enough, right? You might have to make n be what did we have, like 800 million or something ridiculously big before it becomes 800 million to the k, especially if k is a very small number. I think we did 1/5 in that last example. And the reason for that is because if you take the quotient, ln of x over x to the k, as x goes to infinity, we'll get an infinity over infinity form. And by L'Hopital's rule, we saw that we got 1 over x, kx to the k minus 1, and so on. That limit is going to be 0. Okay, so that means, once again, if a quotient has limit 0, we just saw that, then the numerator has to be smaller than the denominator. Okay, so now, we have to pick a good value for k that will make us decide, using the limit comparison test, whether this series converges or diverges. Okay, so what are we going to need to help us? That's for later. Okay, well, we know that if we ignore the ln of n, hide it, we get a divergent p-series. Okay, 5 over 7 smaller than 1, that p-series diverges. All right, so therefore, the k that we should pick should be small enough so that when we replace ln of n with n to the k, the final power that we get in the denominator should still be smaller than 1. Okay, let me write that down. Pick k in the inequality and the limit, so that ln of n, or rather n to the k, times n to the 5 over 7. Okay, so we're replacing essentially ln of n with n to the k, which is n to the k plus 5 over 7. We'll have an exponent, which is still smaller than 1. Okay, 5 over 7 is smaller than 1. We want to add just a smidge to 5 over 7 so that it stays smaller than 1. Okay, well, how about we pick k equals just 1 over 7? Okay, because 1 over 7 plus 5 over 7 equals 6 over 7. Okay, it appears that 1 over 7 would be just small enough so that we get the same denominator. That's the only advantage I can think of for picking 1 over 7. Still 7, but the numerator 6 will give us 6 over 7, which is still smaller than 1. Okay, so in other words, just like we did in our last example, let's make some space here. Thus, in the statement of the LCP, we will let our a sub n be our sequence, 1 over n times n to the 5 over 7, and we will let b sub n, b sub n will be 1 over n to the 6 over 7. Okay, so we replaced ln of n with n to the 1 over 7, and we simplify it to n to the 6 over 7. All right, excellent. So now we need to take a limit. All right, so just like in our last example, we have to check that the limit of the quotient, an over bn, is hopefully, again, an ordinary positive number. Our an is this, So that goes in the numerator. Our b sub n is this. Okay, that goes in the denominator. Okay, so now we are going to get as our quotient, okay, simplify, we're going to get limit as n goes to infinity. This stays in the numerator, but we will flip the 1 over n to the 6 over 7 into the denominator. I'm sorry, into the numerator. So we'll get n to the 6 over 7 over ln of n times n to the 5 over 7. But wait, there's more. So 6 over 7, 5 over 7, we're dividing. 6 minus 5 is 1. Ooh. So there is our n to the 1 over 7 over ln of n. No, oh, wait a minute. Are we upside down? Oh, no. If we have ln of x in the numerator and x to the k in the denominator, we'll get a limit of 0. We are upside down. Oh no, let me scoot up over here. We need more space. Is this a bad thing? Well, let's see. We're going to infinity. Infinity to the 1 over 7, yeah, still infinity. Ln of infinity, still infinity. So again, we can use L'Hopital's rule. And let's see what happens. So before we're going to get 0, I wonder what we're going to get now that it's flipped. So according to L'Hopital's rule, we need the derivative of n to the 1 over 7. Power rule, we'll have 1 over 7. N to the power 1 over 7 minus 1 is negative 6 over 7. And the derivative of ln of n is 1 over n. Okay, by the way, if the n bothers you, I just pretend it's x and write down n whenever you say x. All right, it's really just the same symbol. Okay, same limit, different symbol. Okay, so now we have some flipping to do. That is 1 over 7. And the n to the minus 6 over 7 goes to the denominator. Let me erase this so we don't get confused. So it's n to the positive 6 over 7. But the 1 over n flips to the numerator. So that's just n. But there's more. Now simplify that. N to the 1 over n to the 6 over 7. 1 minus 6 over 7 is 1 over 7. Aha. So we get 1 over 7, n to the power 1 over 7. Okay, that is now simply infinity. So our limit for an over bn is positive infinity. Whoops, I'm in the superscript, so I need to get out of that environment. There we go, I am out. Aha, so surprise, we are not in part A of the limit comparison test. Do you remember where one of the limits was infinity? Let's go look. There it is. If the limit is infinity and our b sub n, it was n to the 5 over 1 over n to the 5 over 7, that is a divergent p-series, then the series that we have, summation of a sub n, must also diverge to infinity. Yep. So this time it's not part A that we need, but rather part C. There we go. Thus, by part C of the LCT, since summation Bn, where is that? There we go. By part C of the LCT, since summation 1 over n to the 6 over 7 is a divergent p-series, our series, which is this, must also diverge to infinity. Ta-da! There we go. All right, so in closing, let's go back this time to the divergence test, or test for divergence, where we saw these two examples. And I'm using the same letters that we used in that video so that you can find them if you want to go back and review that video, which I would recommend. So we have summation n equals 1 to infinity 5n plus 7 over 3n squared minus 2. And remember that the issue here is that the terms go to 0. If you multiply by 1 over n over 1 over n, you will have an n surviving in the denominator, and as n goes to infinity, this gets smaller and smaller, it gets close to 0. And again, if you don't believe me, do L'Hopital's rule. Okay, infinity over infinity, you'll get 5 over 6n. As n goes to infinity, you'll get 0. Okay, so the terms 5n plus 7 over 3n squared minus 2 go to the limit of 0. So the divergence test does not apply. Okay, that's the important takeaway from that video. We cannot form a conclusion about this series, whether it converges or diverges. The test for divergence does not apply. Okay, but now we have the limit comparison test. Okay, so how are we going to apply the limit comparison test? So again, we will let a sub n be these terms. Oh good, it's still there. Well, we need a b sub n. Okay, so we need to manufacture b sub n. Okay, so we don't have cosine, we don't have sine, we don't have ln. We simply have this rational function, 5n plus 7 over 3n squared minus 2. Okay, but here's the thing. Well, we can think about the highest power that appears in the numerator and the denominator. It's almost back to fundamentals. All right, remember back in basic calculus? Oh, I see. Okay, that's practically n, that's practically n squared. Okay, so since the highest power, the highest term in the numerator is n, and the highest term in the denominator is n squared, let us pick, okay, let us manufacture, let us create b sub n to be n over n squared. Okay, so that's practically n, and if you say, well, what about the 5? Well, if you want the 5, go ahead, but I'm not going to do that. It's simpler if we just use n instead of 5n and n squared instead of 3n squared. But once again, by the rules of exponents, basic algebra, that's just 1 over n. Okay, so that will be our b sub n, and now we have to take a limit. Okay, once again, we have to check what is the limit of an over bn. Are we going to get infinity? Well, let's see. The numerator is 5n over n plus 7. 5n plus 7 over 3n squared minus 2. I can't read. In the denominator, we should have 1 over n. Okay, so in the denominator, we should have 1 over n. Okay, again, we have to do some simplification. So we will get the limit of the numerator, and then we will flip the denominator. So that's simply times n. Okay, but, well, what can we do? Let's just distribute that times n to the numerator, so that's 5n squared plus 7n. Okay, so now the highest terms are both n squared in the numerator and the denominator. Okay, so once again, we have an infinity over infinity form, and basic calculus, if you forgot, all we need to get the limit are these two coefficients, 5 over 3. Okay, again, if you doubt me, then do L'Hopital's rule twice. You'll get 10n plus 7 over 6n, And that's still infinity over infinity, so you'll get 10 over 6, which is, of course, 5 over 3. Ta-da! That is an ordinary positive real number. Okay, so we're in part A. Yay, that's the best possible world. And again, we didn't really need to include the 5 and the 3 when we picked our BN, because, yeah, they show up anyway, right? So whether we like it or not, they will play a role in finding the limit. Okay, maybe they will appear over here, or maybe they will appear in the final answer. All right, so, well, oh, wait a minute. What do we know about summation of B sub n? So, I need the summation symbol once more. Here we go. Copy. Since summation of 1 over n is the harmonic series, reminder, it has a name, which we know diverges by part A of the LCT, our series, which is summation of our 5n plus 7 over 3n squared minus 2, must also diverge. Okay, final example. Ooh, and it's not even 1 hour yet. We saw this telescoping series in our video where we introduced infinite series. And in fact, we were able to find the exact sum of this telescoping series using the idea of partial fractions. Okay, remember, you need to align the terms vertically in the right order so that you can see how they cancel. Okay, so what are we going to do with this? I'm going to make it a little bit uglier. Okay, I'm going to put square root here, and then I am going to make it even uglier. So this is now a different example. Goodbye. I'm going to put 5n squared plus 4. Ugly. Okay. And if you say, okay, oh please, how about we put plus 4n plus 7 as well. Okay, talk about ugly. All right, so yeah, we don't want to use, well, number one, partial fractions don't work anymore. They don't work if you don't have a polynomial in the numerator. Okay. And you probably don't want to use the ordinary comparison theorem either. Yeah, kind of nasty. But that's why we have the LCT. As we saw in our last example, yeah, if you just know a little bit of algebra and some basic limit laws, you can easily find that limit. Okay, so again, this will be our a sub n, this ugly thing. Sorry about that. And manufacture. We will need to manufacture b sub n. Okay. So, yeah. Okay. Well, start with the denominator. We have n plus 1, n plus 2. So it looks like n cubed is the highest power in the denominator. So we can easily see that n cubed is the highest term in the denominator. Excellent. What about the numerator? Well, we have 5n squared, and then we have the square roots. Okay, so effectively, the highest term in the numerator is square root of 5n squared. Okay, so yeah, this thing, fine. I'll include the 5. Okay, now n is a positive number. Okay, so this simplifies. We can take it out of the square root. Take it out. Square root of 5 remains inside. But square root of n squared simply becomes n, since n is positive. Okay, it's going to infinity, in fact. Okay, so now we have a good candidate for b sub n by putting this n cubed in the denominator together with this square root of 5n in the numerator. So let us try b sub n to be the fraction where we have square root of 5 times n in the numerator and n cubed in the denominator. And once again, don't just leave it like that, simplify. N cancels with n cubed partially, leaving n squared. Okay, all right, but so fine, there's an ugly square root of 5 there, but who cares? It's just a real number, okay? But we know that our summation of b sub n, okay, it's square root of 5 over n squared. Square root of 5 is just a constant. We can take it out of the summation. We'll get 1 over n squared. That is a convergent p-series with p equals 2. 2 is bigger than 1, so summation 1 over n squared converges. That square root of 5 is just a positive constant. You can take it out of the sum if it bothers you. It shouldn't bother you. Okay, but then, once again, we have to take a limit. All right, finding a limit. Thank you, cut and paste. We want an over bn. This is our a sub n. This is our b sub n. We need that limit. So once again, we're going to flip that fraction in the denominator. Numerator stays the same, but we will multiply instead by the fraction where we have n squared in the numerator and square root of 5 in the denominator. Haha. Okay. So now, what are we going to do? Well, we need to simplify a little bit. So n cancels, that's nice. And we have that somewhat simpler. Okay, so we have n square root of something over n plus 1, n plus 2. All right, again, that's infinity over infinity, okay? And the nasty thing is, well, if you're going to do L'Hopital's rule, good luck with the product rule. All right, you're going to have to take the derivative of n times this. Not something I would recommend, okay? So instead, let's do something even more rudimentary, and I might say creative. Let's factor out the n squared inside the square root, okay? So what are we going to do? We are going to take the n squared out. So there's still a 5 there, okay? So instead of 4n, we will have 4n over n squared, which is 4 over n. And instead of plus 7, we will have 7 over n squared. Okay, so far so good. And then, what's going to happen? Well, again, square root of n squared is simply n because n is positive. So it shows up twice. We use that property twice. One to create the b sub n, one time to find this limit in a cleaner way, right? So we will take that n squared out and it becomes just n. Square root of n squared is simply n. Okay, so now we have n squared in the numerator and we have n plus 1, n plus 2 in the denominator. Okay, so here's what we're going to do. Again, whoops, I forgot. Control C. Okay. We are going to put the n together with the times n over here. So we'll have the n squared. Okay, but that n squared is nice and clean. I'm going to ask square root of 5 to move over here. Okay, so let me just put him aside for a minute. And I'm going to make those two join together. Okay, so look at what I did. Okay, n times n squared, square root of 5, I'm just going to move it here. N plus 1, n plus 2, I'm just going to move it over here. Okay, commutative property of multiplication. Okay, and now we get to use the limit laws, not L'Hopital's rule. Here, as n goes to infinity, we're going to get 0, 0. That becomes square root of 5. Okay, so we're going to get square root of 5 over square root of 5, which is just 1. Okay, but there's more. We also have n squared over n plus 1, n plus 2. Okay, what were you talking about earlier? That denominator is basically n squared plus something. You have n squared over n squared. That limit is 1. Ta-da! So the limit, notice that if we include that square root of 5 in our b sub n, then the limit that we get is simply going to be 1. All right, so now we have a conclusion. Our b sub n is a convergent p-series, so therefore our summation a sub n must also be convergent. All right, both series must must converge, or both series must diverge. So by part A of the LCT, since we know that the series for b sub n converges, our series must also converge. All right, there you go. Under 1 hour, yay! So that is our video on the limit comparison test. Next time, we're going to see a very different kind of test, the alternating series test, where this time we are allowed to make some of our terms be negative half the time. All right, so until we meet again, I hope you enjoy the rest of your day. Bye now.